Hi guys, hope you're having a great day. So today we're going to talk about 2.9, which is the start of the second half of Unit 2, which we're calling Unit 4. And we're going to deal with logarithmic expressions. I'm going to go through this first part pretty quickly because we've all seen a log before back in Math 3. So remember, a log is just the inverse operation of an exponential. So if we think about addition and subtraction, undo each other essentially, multiplication and division, exponential and logs are inverses too. So we'll talk about that connection a little bit more in 2.10, but we're just going to talk about basic properties, how to evaluate them, how to evaluate these expressions. Okay, so remember you might have seen back in Math 3 kind of like the log cycle to kind of evaluate. So if I have something like this, that little b, remember, is called the base. So this would essentially be written as b to the 0th power is equal to 1 if I wanted to change that into exponential form. We know anything to the 0th power is 1, so that's why that works. Same thing over here. This would say b to the first equals b. We know anything to the first power is just itself. And we could keep going with all of these. Now, something you have not seen before is this ln. ln, you do need to be able to recognize from this point on, that's just a log with a base of e. Remember, e is that irrational number. It's about 2.718. It goes on and on and on forever and ever, just kind of like pi. So if you see ln, it's also referred to as a natural log, and it's just a log with a base of e. All right, so let's just practice a few of these, kind of just figuring out why they work. So again, 2, you always start at the base, go to the outside, and back to the inside. So that would, in exponential form, we know that 2 to the 3rd equals 8. Same thing here, 3 to the 1/2 is equal to the square root of 3. We know that's true because raising to the 1/2 power is the same as taking the square root. And we could keep going on all of these as well. Remember, a little reminder, like on part D, if there's a log but I don't see a base written, that is assumed that it's a base of 10. All right, so let's practice converting from exponential form to log form. So again, the 4 is the base, so I'm going to first write log. 4 is the base. It goes to the outside and then back to the inside. So this 3, the exponent, is the answer to the log, is sometimes what you hear in Math 3. So 4 to the 3rd is equal to 64. Same thing on part C, log base 2 of 1 over 32 equals -5. Again, that exponent is the answer to the log. So if I just asked you to evaluate this expression right here, which we'll do in a minute, that answer would be -5. Okay, all right, let's go the other way now. Same idea here. I start at the base, to the outside, back to the inside. So this would look like 5 to the 3rd equals 125. Okay, this would be 1/2 to the -6th equals 64. Let's just remember what we do with negative exponents of why this works. So this would be 1 to the -6 over 2 to the -6, which then could swap places because they're negative exponents. So 2 to the 6th does equal 64. 2 to the 5th is 32. Multiply it by 2 one more time. Divided by 1 to the 6th, well, 1 to the 6th is just 1. Okay. All right. So these right here, these first ones, it says common logarithm. So again, if I don't see the base written, I assume that it's a base of 10. So let's go through the process. Let's go ahead and write in our invisible 10 right here. And we're trying to evaluate these expressions and figure out what do they equal just as a number. So the easiest way to kind of think about this at first, when you're first getting the hang of it, is you're trying to find 10 to what power would give me 100 using my log cycle. Again, we're thinking exponents, not multiplication, so that answer would be 2, 10 to the 2nd. Again, the answer is just the exponent. Okay, same thing here. We're saying 10, because that's my base, to what power equals square root of 10. Well, what does my exponent have to be a square root? We've talked about a lot at this point that should be 1/2. All right, and then right here, so 1,000 is equal to 10 to the 3rd power. So 1 over 1,000 would be 10 to the -3rd. So we're trying to figure out 10 to what power is equal to 10 to the -3rd. Well, if the bases are the same, I know the exponents have to be the same. Okay. All right. There's many different ways to think about this. You could evaluate in the exponent first. So log base 6 of 6 says 6 to what power equals 6? Well, that's just going to be 1. So I get 10 to the first equals 10. I was about to say 1. 10 to the first is equal to 10. Okay, so just evaluating and then raising to that power. Okay. All right, so if you haven't noticed already, okay, we're not doing, or actually we did do 3C. So right here, so whatever is inside my log right here, okay, is always going to have to be positive, okay? So I'm going to write this out and then I'm going to draw the graph, which we'll talk about more in a few minutes. So the argument of the log is essentially what's inside the log. So this right here, oops, I didn't mean to cross it out. This right here always has to be greater than 0. And the reason for that is, if you look at your graph of a log function, it's going to look something like this. It's the inverse of an exponential. If you take the regular exponential parent function and reflect it over the line y equals x, that's what you get. And if you think about why that is, well, if I'm raising to a power, let's say like this is equal to y, b to the y equals x, that's never going to equal 0, okay, because anything to the 0th power is just 1. And that's also never going to be a negative number, because even if I raise to a negative exponent, we know that it turns into a fraction. So that's why, if we think about that argument, what's inside the log will always have to be greater than 0. We're going to expand on that when we talk about the domain of a log function, so keep that in the back of your brain. All right, we're going to do 2 applications of this. Actually, I lied. We're going to do one more like this. Evaluate without a calculator. So question mark, so we're saying 49 to what power is equal to 7? All right, well, let's think about what we know. We know the square root of 49 is equal to 7. So what exponent would that have to be? 1/2. If you haven't gotten the sense that square root and raising to the 1/2 power are equivalent, that should be important because we've done that a lot. Okay. All right, now we're going to do a couple of applications, and we'll do more applications in 214. This is just kind of to dip your feet in the water. So Richter scale is something used to measure earthquakes, and it says the intensity levels of 2 earthquakes measured on a seismograph can be compared with the formula log I1 over I2 equals M1 minus M2, where M is the magnitude given by the Richter scale. So how many times more severe was the 2001 earthquake in India, M1 equals 7.9, than the 1999 earthquake in Greece, M2 equals 599. So we're just going to kind of plug into our formula. This is not a formula that you need to memorize by any means, but you do need to be able to apply it. So M1 was 7.9 minus M2, which was 5.9. All right, remember this really has a base of 10, so I have log base 10 of I1 over I2 is equal to 2. So if I put this back into exponential form, I get 10 to the second equals I1 over I2, which is 100. So it was 100 times greater. Okay, so even though that those are only, the magnitudes are only 2 away, that really represents 100 times greater on this Richter scale. All right, pH scale model is another model that deals with logs. It says it's a scale that measures how acidic or basic a substance ranks. The scale ranges from 0 to 14, where 7 is neutral, and the whole pH below 7 is 10 times more acidic than the next higher value. All right, so balsamic vinegar has a pH of 2.4, and a box of baking soda has 8.4. What are their hydrogen ion concentrations? So if I have right here the pH, which is 2.4, is equal to negative log of my hydrogen ion concentrations. Yeah. So I'm going to go ahead and solve for that. So I'm going to divide both sides by -1, and I get negative 2.4 equals log of my hydrogen ion concentrations. Remember, that's a base of 10, so I get 10 to the negative 2.4 power is my hydrogen ion concentration for the balsamic vinegar. All right, then I have the baking soda. Okay, so again, that's balsamic vinegar. Baking soda of 8.4, so we're going to follow the same sort of idea here. and I get negative 8.4 equals log of my hydrogen ion concentrations. 10 to the negative 8.4 is my hydrogen ion for the baking soda. All right, so it says how many times greater is the hydrogen ion concentration of the vinegar than the baking soda? Okay, well, the vinegar was 10 to the negative 2.4, and the baking soda was 10 to the negative 8.4. So negative exponents on the top can go to the bottom. Okay, so we get 10 to the 6th power. Okay, so 6 orders of magnitude greater. And that just comes, of course, from that exponent. Okay. All right, so hopefully at least the first part of this was kind of review from Math 3 of just evaluating, putting into exponential form and log form and all of that fun stuff. We will deal with these models like Richter scale a little bit more later, but it was just kind of to get your feet wet on what those kind of look like. So hope you have a great rest of your day.